Most of my research is on the material science of polymeric materials, so plastics and rubbers and stuff like that. And mainly we do two things in my lab nowadays. One of those is the science of multi-phase plastics or multi-phase polymers. So what that means is that many polymers used in daily life have other things added to them, oftentimes particles. A good example would be tire rubber, which has 25–30% of carbon black particles added to it. What we do a lot of is trying to understand how we can control the structure, the microstructure of these polymeric materials, and then try to develop new materials with new and interesting properties based upon it. So let me give you a simple example of what I mean by controlling microstructure. So here I have just regular sand that I purchased from Home Depot. And you can see I can easily pour it into this container because it's dry. Now when I add a little bit of water to it, and shake it up, this is now wet sand, and no surprise, it is much harder to pour. And we know that we can build a sandcastle out of this. So this water is acting like it is going to produce little menisci that hold the little sand particles together. And so there is a big change in flow properties because this sand has now formed a big network where all the particles are touching each other. So now imagine what would happen if the continuous phase of this sandcastle is not air but a plastic. And then further imagine that you have this plastic now that has this network of particles that is being held together by something else, right? So this is the kind of thing I mean by structure control, that this system now has two phases that are continuous. Obviously the plastic is continuous, just like the air would be in a sandcastle, but the particles are all touching each other. So now if the particles were made of metal, you can now see that this plastic would have become conductive, right? Because all the metal particles are touching each other. So that's the kind of thing that we mean, that just by taking metal particles, a plastic, and something else to cause these particles to aggregate together, you have made a plastic that is conductive, but most importantly, you made it just by mixing it up. That's the kind of thing that the plastics industry is really good at doing. Mixing it up, processing it, extruding it, maybe you could 3D print it. So perhaps soon enough we will have ways of having circuitry that is built into plastic parts, because this is now a conductive plastic that can flow. So we are very serious about being an experimental research group. So we really like to do things. We are very much guided by theory, but what my students really learn how to do is how to think of what experiments to do, and maybe even more important, what experiments not to do, and not to waste time on them. I always say that talk is cheap, and so we discuss 10 experiments, and at the end of it, we find that 8 of those are really not worth doing. And really we want to focus on those 2 that are worth doing, that are going to teach us something and be useful for testing our ideas very carefully. What is wonderful about Swanson Engineering that it is not siloed. So much of my research is very much related to mechanics. It's close to mechanical engineering. It's sort of interdisciplinary, and Swanson Engineering does not create any silos. I am free to take students from any department I want. I can work on topics that are of interest to me. And the fact that all of engineering is in a single building is a huge advantage. I've been at various other places before this, and none of them had this sort of very nice idea of putting everybody together in one single building to break down all the barriers.